Today I'm going to be going over KVL, which is Kirchhoff's voltage law. All Kirchhoff's voltage law states is that the change in voltage around any closed loop in a circuit is equal to zero. What that basically means is that if you start at one node, say this node right here, you walk all the way around the circuit, counting up the changes in voltage, ending at this node, the change in accumulated voltage is going to be zero. Now, the best way I can think of to explain this in another way, like a good analogy, is like hiking or climbing a mountain. So another way you can describe voltage is like potential. So say you start on the ground. If you go up the mountain, there's some change in altitude or change in potential. If you come back down the mountain and end at the same elevation you were when you started, your change in potential or your change in height is zero. And so I'm going to be talking about KVL through a more specific example. So this is example 3.2 from Engineering Circuit Analysis by Haight. And all it's asking is to find the voltage Vx and the current Ix. Now, in your circuits classes, you've probably heard of something called the passive convention, which is where you always write a minus sign if you hit a minus sign in a loop. But I'm going to be using the active convention for the first part of the video, just because it's more intuitive for me. And so I'm going to start my loop at this node that I've circled down here. And all I'm going to do is walk around the circuit in the direction of this loop right here. And I'm going to count the accumulated voltage changes until I come back to this loop. And so I like to think about voltage sources as rises in voltage. So this is why I use the active convention. So when I hit this 5 volt independent voltage source, I rise 5 volts. So I'll write plus 5 volts. And then I'll move on to my next change in voltage, which is another rise in 7 volts. So plus 7 volts. Next, what is going to happen is the current is going to hit the resistor. And I like to think about resistors as drops in voltage. And so I'm going to use Ohm's law to represent the change in voltage across the resistor. So I'm going to write minus Ix times R. And then all that equals 0 because I'm returning to the node that I started on. And so I rose 5 volts, I rose another 7 volts, and then I dropped voltage across the resistor, and I ended back up in the same spot. So all you do at this point is solve for Ix, which is the only unknown in the circuit since we were given R. So 12 volts equals Ix times R. So 12 volts divided by R equals Ix. So that's 12 volts divided by 100 ohms equals Ix, which means that Ix equals 0.12 amps. So that will be your answer. And the next part of the video is finding the voltage Vx. Before directly finding the voltage Vx, I want to go back and talk a little bit about the resistor itself. So as I mentioned, the resistor has a voltage drop across it. What that means is that the terminal that the current is entering in has a higher potential than the terminal that the current is leaving. And that is the direction of VR. So it's VR with plus minus being this way. And as you can see, Vx has the same direction as this smaller model here. The voltage at this terminal of the resistor is less than the voltage at this terminal of the resistor. So that means that we know that Vx has to be positive in this circuit. And so I'm going to rewrite my loop, but using Vx instead of Ohm's law in order to find it. So as I stated, we get a rise in 5 volts. You go up 7 volts. And then, as you can see here, you drop Vx. So minus Vx. And then as you end back at the node you started at, all that equals 0 because your change in accumulated voltage equals 0. So now we just solve for Vx. So then Vx equals 12 volts. Just using algebra. So next what I'm going to do is I'm going to repeat the whole problem, but I'm going to use the passive convention. So with the passive convention, you do the same exact KVL loop that I mentioned earlier, but anytime you hit a minus sign, you write it as a negative quantity, and anytime you hit a plus sign, you write it as a positive quantity. And I just want to mention the model for the resistor again. the terminal that the current is entering will always have a plus sign on it, no matter what the problem actually states. So I'm going to be doing, in this problem, it just happens so that the terminal where the current is entering also has a plus sign. So it's not going to be an issue for this problem, but it might for other problems. So I'm just going to write a KVL loop this time using the passive convention. So I'm going to start at this node right here, and as soon as I come to this voltage source, I hit a minus sign. So I'll write minus 5 volts. As I keep walking around the loop, I hit another minus sign with minus 7 volts. Finally, when I hit this resistor, I hit a plus sign with plus Vx. Actually, I'm going to write it using Ohm's law instead. So I hit a plus and then Ix times R. And that equals 0. So just like in the last problem, I'll solve for Ix. Because I move over 5 and 7 to this side. So just like with the active convention, you get the same exact answer for Ix. Now I'm going to find the voltage Vx. So I'm just going to do this by writing out the loop in the same exact way using the passive convention. So you start here, you hit a minus sign, hit another minus sign, but this time you hit a plus sign, so you write plus Vx. And since you started and ended at this node, all that equals 0. So all I'm going to do is solve this out. So minus 12 volts plus Vx equals 0. So Vx equals 12 volts. So that would be how you solve the problem using the passive convention. Now what I'm going to do is I'm going to reverse the direction of Ix and Vx to show you what to do in the case that the current and voltage doesn't line up with your intuition. So this is the exact same problem from the earlier part in the video. All I did was switch the direction of Ix and Vx. Now this might go a little bit against your intuition because you would assume that current is rising up and then dropping across the resistor, which is the exact opposite direction of Ix and the exact opposite direction of Vx, because it's saying that this potential is higher than this potential. But what I'm going to show you in this problem-solving process is that you can actually ignore the reference values that they give in the circuit. You can solve the problem however you want, compare your answers to their reference directions, and then get the answer that way. And so this is a little confusing. I'll show you how to do it in the way I'm explaining. So all I'm going to do is I'm going to write my loop as normal. So I'm going to start at this node right here, and I'm going to circle around the circuit this way. And I'm going to pretend that this is some imaginary current IL. So I'm saying that IL is going clockwise in this circuit. And I'm going to use my loop and I'm going to write my loop using IL. So let's write it out. So I'm going to be using the active convention in this video. So I'm going to write plus 5 volts plus 7 volts, and then a voltage drop across the resistor using IL minus IL R equals 0. I'm going to solve for IL. Now this is the same process as earlier in the video. So I get an answer of 0.12 amps. However, this isn't the answer to the problem. As you can see, IL and IX are simply facing in the opposite direction. And so all I do is I say that IX equals negative IL, because IX and IL are again facing in the opposite direction. And so I can write out that IX equals negative 0.12 amps. And that would be my final answer for Ix. So all I did was I wrote a loop based on what my intuition was telling me. I solved for that current, and I compared that current to what the problem gave me. If they faced in the same direction, then I know my answer is positive, but since they face in the opposite direction, I know that my answer was negative. And so next, I'll be solving for Vx. The next thing I'm going to be doing is solving for Vx in this circuit with the direction switched from the previous problem. So again, what I'm going to do is just assume a direction for Vx, or Vr, which is the voltage across the resistor. And what my intuition is telling me is that if I have IL going into this terminal of the resistor, Vr is going to be facing this way. This is just the simple model of the resistor. And so I'm going to be solving for Vr using Ohm's law. So Vr equals IL times R. So that means Vr equals 0.12 amps times 100 ohms. So Vr equals 12 volts. I'm not going to circle that. However, what the problem says is that Vx is facing this way. Vr is facing this way. If I were to write it on the circuit, it would be like this. I'll erase this. As you can see, Vr and Vx are facing in opposite directions. So all that tells me is that Vx equals negative Vr. So Vx is going to be equal to negative 12 volts. Now what we can do to confirm this answer is to actually just write a loop that's without using the current in the loop. So I'll go ahead and do that now. So if I were to write a single loop in the, like following the outer circle, I would get this. So I'm going up 5 volts, going up 7 volts, and I'm actually going up Vx volts. That equals 0. So I'm just going to solve for Vx here. 12 volts plus Vx equals 0. So Vx equals negative 12 volts. And that's the same exact answer I got previously. So the point I'm trying to make in this video is that the problem could give you a direction that maybe goes against your intuition. And what you do in that case is you simply just assume a loop current direction, and if your answer is positive, then what you assumed and what they gave you would be facing the same direction. If your answer is negative, all that means is that your assumption and their reference current direction just face in different directions. So this is example 3.3 from the same textbook, and it's asking to find the voltage Vx and also Vr2. And so the first thing I'm going to do is I'm going to write a loop in this direction. And that's because I can see that in this loop, I only have one unknown and I have two known values because both of these voltages are given to me. So I'm going to start at this node and end back at this node. So looking here, I have a negative 4 volt drop across this resistor because it's going from plus to minus. So this is minus 4 volts. I have a rise in 36 volts. And then I have a drop of Vr2. That equals 0. So if I just solve this out, I get Vr2 equals 32 volts. So that is the first part of the problem solved. And so I'm also going to do this in the passive convention. So if I start at this node, I hit a plus sign, so plus 4 volts. I hit a minus sign, so minus 36 volts. And then I hit another plus sign, so plus Vr2 equals 0. So that means Vr2 is just equal to 36 minus 4. So Vr2 equals 32 volts. As you can see, you get the same answer with the passive and active convention. And another thing you can notice is that the loop equation for the passive convention is just negative 1 times the loop equation for the active convention. So they are the exact same thing. It's just I find the active convention a little bit more intuitive, but you can do whichever method you choose between these two. So next part of the problem is to solve for the voltage Vx. In order to do that, I have to write a loop of the right-hand part of the circuit. And as I've drawn here, my loop is going to start at this point B, going around the circuit this way, and then back to B. And so I'm going to start here, and then I'm going to write out all my voltage changes, and that should equal 0 per kVL. So first I'm going up in voltage VR1. I'm dropping VS1. I'm dropping V2. I'm increasing by 14 volts. Going up again by 12 volts. And then dropping by VR2, which I found from the previous problem. So the point of this loop is to solve for Vx. However, an issue we have here is that, first of all, Vx isn't in our equation, and we don't know any of these values. VR1, VS1, V2, we don't know any of those values. So what we need is another equation that eliminates some of these variables. And in order to do that, all you can do is just write another loop. And so one thing that you can develop the intuition to do is write a loop using like the difference in voltage between two nodes. And you can do that one of two ways. The first way, if you wanted to eliminate some of these variables, is you could write a smaller loop here. And I'll show you how to do that. So if I were to write a loop here, it would be going up VR1, dropping VS1, dropping V2, and since this loop just involves this part, I'm actually dropping Vx from A to B. And since I'm starting at B and ending at B, I can do this. I can just ignore this side of the circuit. So I'm dropping Vx from A to B. So minus Vx equals 0. And so if I solve for Vx, I get the following. I get that Vx equals VR1 minus VS1 minus V2. And what you can see is that I can just take that and replace it in this first equation. And since I know all these values, I can actually just solve straight. I can just go ahead and solve for Vx. So I can write that out. So all I'm going to do is I'm going to erase this side right here and then put in Vx. So if I solve for Vx, I get that Vx is equal to VR2 minus 26 volts. Just adding 14 and 12. So that would mean Vx equals 32 volts minus 26 volts. So Vx equals 6 volts. So that's the same answer that's listed in the textbook. And I'm also going to solve this another way. I told you that there was another loop that you could draw to also solve the problem. And this would actually limit the number of the amount of time taken. So like I said, if you know the voltage difference between two different points in the circuit, you can just ignore the circuit components completely. So I'm going to start at B. I'm going to go up Vx. I'm going to go around this way and end at B. And so since I'm starting and ending at the same point, this loop is completely valid. So I'm just going to ignore this side of the circuit since I know that the difference between this point in the circuit and this point is Vx. So I'm going up Vx here, going up 14 volts, up 12 volts, and then dropping VR2. And so that's the same exact process, and you get that it equals 6 volts. That Vx equals 6 volts. So that's how you would solve this problem.